So here's kind of the last big thing on forces, and this is inclined planes. So up to this point, we've only dealt with flat surfaces, which is kind of fitting because we're in Kansas, okay? Yeah, we have a lot of flat surfaces. So they've actually done a study, like if you compare Kansas to a pancake, Kansas is actually flatter than a pancake on an atomic scale. Okay, seriously, I mean, if you look at the surface of a pancake, it has like little pockets and stuff in it. And on a relative scale, Kansas is flatter than a pancake. Well, I'm just saying. So when you get into inclined planes, there are certain things that are still going to be the same. The gravitational force is still going to be mg. Okay. So let's say, for example, I've got this little cart here, and let's say that it, just to make the math easy, let's say that has a mass of, it's not, but it's just going to make the math easy. Let's say that that has a mass of 1.02 kilograms. I multiply that by g, I get 10 newtons. Now, what you'll see is that when you calculate this weight, don't worry about making that positive or negative. This is just a gateway force. You're just going to use that to find out a whole bunch of other things. So literally, when you calculate the weight, and that's how all these problems start, you're always going to be given the mass of the cart, whatever it is, okay? You always start with that. So you're going to sit there and go, okay, that's 10 newtons. Simple. Do not make it complicated. Do not make it negative. Just get the number and then decide. Now, here's the situation. So if I take this cart and I put it here on a flat surface, it doesn't accelerate. Why? One of two reasons.
There's no force.
Either there's no forces acting on it at all, or the forces are balanced.
Forces are balanced.
Yeah, there's gravity pulling down, you got the normal force from the table, all the forces are balanced, right? Simple as that. Now, if I take that same cart, though, and I put it on a book, and I lift that book up at all, even if I just give it the slightest bit of angle, what does the cart begin to do?
Accelerate.
The cart begins to accelerate, right? So, and if I lift it up even higher, what's going to happen to the acceleration? It's going to increase, right? So there's obviously a direct relationship between the angle and the amount of acceleration. So if you were to draw a graph, let's say, here's your angle. Here's 0, 0, and this is your acceleration. Let's say that's 90 degrees. So if you call this 0, okay, which we are, what's my acceleration going to be?
0.
0. Now, if I lift this up a little bit, I get an acceleration. I lift it up higher, I get more of an acceleration. So what's that graph going to look like?
Straight sloping.
Yeah, it's going to go something like this, right? Now, if I were to go all the way to 90 degrees, okay, completely 90 degrees, and let go of it, what would the acceleration be?
9.8.
Acceleration due to gravity, right? Okay, 9.8 meters per second squared. So I know at 90 degrees, I get an acceleration of 9.8 meters per second squared. And so as my angle gets steeper, my acceleration gets bigger. Now, if you look at F equals ma, as I lift the board, am I changing the mass? It's staying the same, right? So as I lift the board and make it steeper, what's going to happen to the value of the force?
It's going to be the
Same thing. So if you were to draw a graph of force and angles, it would mirror that same thing. Because as the angle gets bigger and bigger and bigger, you would create more and more force. So here's what we know right now, is that if you increase theta, which is going to be the angle, I get a bigger force and I get a bigger acceleration. And those have to go hand in hand. I can't have a bigger force creating a smaller acceleration. That'd be cool, right? Oh, the harder you hit something, the slower it accelerates. Pop.
So that's force net, right?
Yes.
Okay. Yeah.
That's force net. We'll go, force net's a whole other story we'll get into.
Okay. Well, okay.
We'll get into it. Now, this particular force is what we're going to call force parallel. So I need to do a little bit of trig right quick, okay? So when you look at inclined planes, there's three forces that are always present, okay? One of those is going to be your normal gravitational force, which is just mg. And that's just going to act straight down, okay? So your gravitational force always acts straight down. Technically, it's toward the center of the Earth, okay? But we're just going to call it down, okay? Because that gets weird, because if you're on the South Pole, it's actually like falling up. So on the equator, it falls sideways, okay? But within our frame of reference, we're going to say it's going to fall down. Now, again, do not, when you calculate weight, I cannot emphasize this enough. When you calculate Fg, you just get a number and call it good, okay? Now, there's two ways you can draw this next triangle. I'm going to draw both of them. You pick whichever one you like best in terms of how you draw it. So we're also going to have a side over here, which is going to what we're going to call the normal force. And then we're going to have a force over here, which is what we're going to call force parallel. So this is our parallel force, and this is our normal force, okay? Now, the beauty of geometry is that, like, let's say, for example, that's a 30-degree angle. So whatever angle this is, and if you go through the proof of using, like, alternate interior angles and congruencies and things like that, which is horribly boring. But if you go through this proof, you'll see that whatever angle this is whatever angle this is. Okay, so that makes the geometry simple. It isn't like it's, oh, one's 30 and the other one's a complementary angle and it's 60 or something like that, or it's half that, okay? So whatever the angle is on the incline is whatever the angle is inside that triangle. So in that case, that's going to also be a 30-degree angle. Now, what the weight represents is the hypotenuse. So that side that's acting straight down is the hypotenuse, okay? That's going to be important. You're always going to know the hypotenuse. So I'm going to draw this a little bit bigger. So with that first situation, that thing weighed 10 newtons. So then I'm going to have a side, this side, which is going to be force normal. And then this is going to be my force parallel, and this is going to be a right angle, okay? And this angle in here is going to be a 30-degree angle, okay? Or whatever it is, okay? I just have to pick a 30-degree angle. So, here's the story. Back in. The 10 newtons is the hypotenuse. I know this angle. I want to find the side opposite, which is this force parallel. So what trig function am I going to use to find that force parallel?
Is it sine?
Fantastic. So I know the sine of 30 degrees is going to equal that side opposite, which is force parallel, divided by my hypotenuse, which is the weight of the block. So I'm just going to put this in terms of like generic things. So my force parallel then is going to be Fg sine theta. Sometimes you'll see it written as force parallel equals mg sine theta. Okay? Both of those mean the same thing. So force parallel, you use sine because it's the side opposite that angle. Now, if we use parallel, and that we're using sine, what are we going to use for a force normal, Vitor? Sine, cosine, or tangent?
For force normal, if
Yep.
we're using the 30, then cosine.
I'm still
Adjacent.
using that 30-degree angle. I still know the hypotenuse.
Yeah, adjacent. So it's cosine.
Okay? So my normal force then is going to equal Fg cosine theta. Now, here's the beauty of trig. So if you're on a flat surface, what's the sine of 0 degrees? What's the sine?
0.
It's either 1 or 0.
0.
0. Okay? So the sine of 0 degrees is
0.
0. So on a flat surface, how much force parallel do you have?
0.
0.
0. That's why it sits here. Oh, that's kind of cool, right? Now, if I go to 90 degrees, what's the sine of 90 degrees?
1.
1. If I go like this and drop it, guess what? My force parallel is the same as the weight of the cart. Okay? Makes sense. And if I'm somewhere in between, it's somewhere between 0 and the weight of the cart. Okay? Now, let's talk about the normal force. And when we started this discussion about forces many weeks, many days ago anyway, I said, when I introduced normal force, I said it's just going to be Fg cosine theta. And I said, don't worry about the cosine theta part, because we're going to be on a flat surface. Because what's the cosine of 0?
1.
1. Okay? So the cosine of 0 has always been 1. So technically, we have always been multiplying by the cosine of 0, but we don't write it down because it's just 1. It's like, really, Brickham? Do we need to write down cosine of 0? It's just 1. So that's why we don't do it. But here's the biggest paradigm shift that you have to make on inclined planes, okay? Listen to me. This is the biggest paradigm shift that you have to make. Now when you calculate force normal, you just can't say, oh, force normal is the same as the weight of the block, okay? It's not. Now you have to take that angle into account, okay? So on any inclined plane problem, do not just go, oh, force normal is the same as the weight of the block. Can't do that. You have to take that angle into account. So with this one, I need somebody to do this calculation. So I need to know what that normal force is going to be. So that normal force, somebody take 10 newtons times the cosine of 30 degrees.
Is it 5 newtons?
What are you saying?
10 newtons times the cosine of 30.
8.66.
Square
8
root of
point-
3 over 2.
66.
Newtons. Okay.
Over 1, right?
So now I'm going to redraw this thing a little bit bigger. So we've got a 10 Newton force acting straight down. We've got a force parallel, and this is at a right angle. So your force parallel is going to be the sine of 30 times 10. Trust me, that's 5, okay, because the sine of 30 is 0.5. So force parallel is going to be 5 newtons. And my force normal is going to be 8.66 newtons. Now, on any inclined plane problem, whether there's friction, push, pulls, squirrels, penguins, it doesn't make any difference. Those are the 3 forces you will always have on every inclined plane problem. Always. Force parallel, force normal, the weight of the object. Okay? Those are the 3 will always be there. Now, at this point, let's make a couple of observations. So if I set this thing at a 30-degree angle and let go of it, it's clearly going to accelerate, right? Okay? It's going to accelerate. So that means it's an imbalanced force because I'm going to create an acceleration, right? So the first decision that you need to make is that how do you want to define the system? Do you want to define downhill as being negative, or do you want to define downhill as being positive? Ask them, how do you want to do this? Do you want downhill to be negative or positive?
We'll do downhill negative.
Okay, fantastic. So, in the Aspen coordinate system, this force parallel is going to be a negative 5 newtons. Now, once you set a parameter within a problem, you can't change it. So everything is going to be going off of the Aspen coordinate system. Downhill is going to be negative. Now, on the next problem, I go, yeah, I want downhill to be positive. Cool. You can do that, okay? I don't care. It makes me no difference. But once you define a system, and you say, okay, Aspen has chosen downhill to be negative, everything is going to go off of that coordinate system. So imagine there's like an X and Y coordinate system. Anything going downhill is going to be defined as negative. Anything going uphill is going to be defined as a positive value. Okay? Now, chart. So, with the charts, we're going to add a layer. So, we've already talked about force applied. That's like if I take the cart and I push it up, or I, do something like this. Okay, some external force. You can have force friction, but now we're going to have a new one of force parallel, and we're still going to have net force. So what's going to change from what we've done so far? What we've done so far, we've either talked about the friction mafia, okay, like this. We've talked about the gravity mafia when you launch something up in the air. But now we have to talk about the parallel mafia, okay, which is actually a subdivision of the gravity mafia, okay? Because if you don't have the gravity mafia, you don't have force parallel, okay? So force parallel is just a subset of that. Now the other absolute rule, and we're not going to do this for obvious reasons. I said, okay, class, here's the lab that you're going to do today. I want you to set up a book on an inclined plane. And I want you to hold a cart, and I want you to let go of it, and I want you to observe what happens. For the next 30 minutes, go. Guess what's going to happen every time? It's going to roll downhill. I guarantee you, if you do this long enough, it's like all of a sudden, it starts to move up the hill. Okay? No. Every time, which direction is force parallel going to act? Downhill. Every time. Okay? You are never going to get off the ski lift in Colorado, and then gravity is going to push you up the hill. Okay? Which would be cool, don't get me wrong. Okay? Even in Colorado, gravity is not going to make you higher. They have other things for that. Gravity, I just don't act like you all don't know. It's Colorado, Rocky Mountain High. It has a whole new meaning. So I can't make that. This is why I don't teach in Colorado for any number of reasons, because the kids will be going, dude. Okay? Kansas, you all think that's funny. The kids in Colorado are going, sup? Yeah, they're, whoa, Mr. Burkia. Okay, so that's why I teach in Kansas and not Colorado, for any number of reasons. So here's the deal. So force parallel, no exceptions, always acts down the hill. Now, in the Aspen system, downhill is going to be defined as a negative value. Okay? If you like downhill to be positive, it's like, oh man, I like downhill. I'm a downhill kind of person. Fine. In your world, downhill is going to be a positive value. So notice I didn't say that force parallel was always negative. All I said was force parallel always acts down the hill. You have to decide if you want to make it positive or negative. Okay? That's in your reality. Okay? So, situation number one. Well, you can draw this like an enclosed triangle. And some people like that because they like to see the geometry of it. Okay? So if that's how you like drawing your triangles, draw your triangles like that. That's cool. Okay? Now, what some people like to do, because they like to see how the forces actually act. So what they'll do is they'll draw the box. They'll draw the gravity pulling down. Okay, there's 10 newtons. There's my FG. And then what they'll do is they'll draw it more like a free body diagram where these are the direction of the forces that are actually acting on the block. Okay? So the advantage of this is that it gives you more of a visual in terms of how the forces are actually acting. So like this surface here is actually providing this normal force, which is overcoming the force of gravity. This force parallel is actually acting down the hill. So if you like this one, because it's more of a representation, that's cool, okay? I don't care. This one, it's a little bit harder to see the geometry in terms of what's a 30-degree angle and what's your force parallel and things like that. But if you understand, oh, force parallel is FG sine theta, force normal is cosine theta, then it doesn't matter, okay? But here's what's going to be important, and y'all are going to draw these on the assignment today. So listen to me. Your force parallel always acts, oddly enough, parallel with the surface, downhill, okay? No exceptions. Your normal force, and this is the one that kids tend to screw up. Your normal force does not act straight up. Your normal force acts at a right angle to the surface and points out this way, okay? So you all were used to drawing your normal force straight up because you all have been on flat surfaces up to this point, okay? This one, you need to draw that force normal like this, pointing out like this, so that that makes a right angle, okay? So, force parallel, so this will make a right angle between that, no, excuse me, this will make a right angle between like the bottom of the ramp and this. This is going to make a right angle between the surface and that's going to be acting straight down, okay? I don't care how you draw your system. That's completely up to you. Now, so here's a cool way you can kind of demonstrate this. So, kind of a one-trick pony, but it's a cool trick. So what I've got here is, down in here, I've got a little scale, okay? It's a cute little scale. Turn it on, and it measures in grams, okay? So I've got a little card here, okay, has wheels, and I've got a 50-gram mass that I'm going to put inside of here. So I'm going to hook that up. And right now, that scale is reading 86.7 grams. Okay? So the scale is reading 86.7. Now, over here, I've got a spring scale. And it has a plunger in here, and this measures newtons. Okay? So right now, there's no tension on this spring. Okay? It's zero. So this is a good way of modeling the force parallel and the normal force. So the scale is balancing out the force of gravity. It's measuring it in grams, but we could put it in newtons. In this case, the scale only measures in grams. So basically, gravity is pulling down, and the scale is saying, hey, I'm providing an upward force that I'm going to call a certain number of grams. Okay? Cool with this? So what I'm going to do is I'm going to lift this up. Okay? So I'm going to lift this up. Obviously, the car's going to try and roll down the hill. Okay? So here's the million-dollar question. As I lift this up, what's going to happen to the reading on the scale on the bottom? And what's going to happen to the reading here? So they could both increase. They could both decrease. They could both stay the same, because gravity isn't changing. The reading on the scale here could get bigger. The reading on the scale could get smaller. The reading on this could go negative, and the reading on that scale actually gets bigger. So they both stay the same. They both get bigger. They both get smaller. One gets bigger, one gets smaller. Those are your options. Pop.
The one on the scale is going to get smaller, and the plunger is going to get bigger.
Why is the reading on the scale, why is that scale going to get smaller? Is gravity just doesn't affect it as much?
It's because the parallel force is increasing.
Correct. So you can think of this in terms of like vectors. So as I lift this up, let's talk about one thing. So if I lift this up, what's happening to the weight of this system? Do not make this difficult.
It's
It stays the same. Gravity is still pointing down at the exact same amount of force, right? Okay. But if you notice, the reading on this scale has gone from 0 to 0.25. Excuse me. No. But Pop's right. The reading on the digital scale has dropped to 75.2. So this, when it was flat, we were about at 85. Now we're down to about 75. Because basically what we're doing is we're transferring these vectors. So I've still got the same amount of weight pulling down, but now I'm taking a component of that weight, and I'm taking a component of that, and I'm making that try and make that cart pull down the hill. The scale, though, because part of that weight, that value is now acting down the hill, the scale doesn't have to provide as much force because we're shifting it. So as I lift this thing higher and higher and higher, the scale, that plunger scale has gone up to like 0.5, and the reading on that on the digital scale has dropped to like 39 grams. So as I lift this thing higher and higher and higher, the reading on this plunger is going to get bigger because I've got more and more force parallel. But the reading on the scale is going to go
Smaller.
Now, if I go all the way to vertical, what's going to be the reading on the scale? Zero, because there will be no component of that weight acting into it. It's all going to be parallel. Okay? So we go all the way to 90. Lo and behold, we got no reading on the scale, and we're up to like 0.75 newtons on that plunger. Got the idea? Okay. So, I love that little hole. Little toilet's cool. Okay. Let's stop with that. Okay, stop that for a second. Stand up. Take 0.
Yeah.
That's harsh. Okay. All right. So what we're going to do is we're going to go through different permutations on how these problems can play out. We'll start with the easiest. We'll end up with the most complex. So you got a 1.02 kilogram block is released on a frictionless inclined plane, and the angle is 30 degrees, and we want to find the acceleration. So there's a couple of things that I would do. If you gave me this problem and said, hey, what's going on here? Literally, here's the first thing I would do. I'd come in here and draw my inclined plane and go, okay, I got gravity acting down, I got my normal force, and I got my force parallel. Do you want to stick with force parallel being a negative number?
Yes.
Okay, so I know this is going to be some negative number. Now, it's frictionless, okay? So I don't have to worry about the frictional mafia, right? There's no applied force, so basically what we're saying is that I'm going to take this 30-degree angle, I'm going to take this cart, which is frictionless, and I'm going to let go of it, and I'm going to see what the acceleration is. So, because I just let go of it, there's no push, there's no pull, there's no rocket engines, there's no squirrels, penguins, nothing, okay? So, when in doubt, chart it out. So you're going to have potentially a force applied, potentially a force friction, potentially a force parallel, potentially a force net. Okay? Now, the same rules apply. Back up. I'm asking you to calculate an acceleration. So right away, what do you do? What do you know your net force is not going to equal?
Negative.
I'm asking you to calculate an acceleration. What if your net force equals 0? What's your acceleration going to be?
0.
0.
So,
Yeah, so by virtue of the fact that I'm asking you to calculate an acceleration, my net force is not going to equal 0. So in this situation, it's frictionless. I don't have to worry about that. Okay? I'm not pushing, I'm not pulling, nothing. My applied force is going to be 0. So if you go through the math, because it's a 30-degree angle, this is the math we've already done. 1.02 kilograms, force weight is 10 newtons. That means my force parallel is going to be -5 newtons. Okay? That's the only game in town. So when I let go of this cart like this, That negative 5 newtons is the only force acting on it. There is nothing else, okay? So, my net force is just going to be negative 5 newtons. Now, Jackson,
Yeah.
I know my net force. How can I calculate my acceleration?
Divide the net force by your mass.
Fantastic. So, somebody take negative 5 newtons and divide that by 1.02 kilograms.
4.901. 902.
Negative 4.9,
Oh, two.
call it negative 4.90 meters per second squared. Okay? Now, here's the most common misconception. Everybody goes, whoa, that's half the acceleration due to gravity. And everybody thinks that should happen at 45 degrees. Oh, 45 degrees, that's halfway up. That's when your acceleration should be negative 9.8. Half your acceleration actually occurs at 30 degrees. Now, if you want to get clever, if you're a pure mathematician, okay, if you're a pure mathematician, here's what you can do. Now, you have to keep in mind, this is a cool trick, but it's a one-trick pony, and it only works under one circumstance. So basically, if there is no friction and there's no applied force, your force net equals mass times acceleration, which equals your force parallel, which is mg sine theta. So what's going to happen is that your masses will cancel out, and A equals g sine theta. So if there is a pure frictionless surface, and again, this is a one-trick pony, and it's a cool trick, but don't think, oh, I can use this on any inclined plane problem. No, this only works if it's a frictionless surface. Now, I don't know if you all remember, you all have seen this equation before? We did that very first inclined plane lab where you push the cart up the hill, and I said, this is how you're going to calculate your theoretical acceleration. This is where it comes from, okay? The idea that your force parallel is the only force. So if you do the same thing, if you take 9.8 meters per second squared times the sine of 30 degrees, you're going to get that 4.9. So this is a handy shortcut, and it's a cool trick, but use it sparingly, because it only works if there's no other forces acting on this thing. Now, I'm going to change it up a little bit. So, we're still going to have the same 1.02 kilogram mass. It's still a 30-degree inclined plane. It's still frictionless. But, now I want to pull it up at a constant velocity. Okay? So imagine this. Here's an inclined plane, 30-degree angle. I want to push it up at a constant velocity. I don't know how much force I'm going to need. So what are the two most important words in this problem?
Constant velocity.
Constant velocity. My net force is going to equal?
Zero.
Zero. So now, set up your chart. Okay? So here's what we've got going. It's weird. I figured out if I double tap the pin, then it starts to work. It's weird. Okay. So I've got my FG. I got my force parallel. I got my force normal. Now, Keith, which direction is the force going to act? Up the hill, down the hill?
Up the hill.
Up the hill, right? So I want to push this thing up the hill at a constant velocity, or I want to prevent it from rolling down, and I'm going to let it roll down the hill at a constant velocity. Same idea. So no matter what, my force applied is going to act up the hill. So now at this point, I've got four forces involved: normal, parallel, gravity, force applied. So now set up your chart. Force applied, force friction, force parallel, force net. What do you want your net force to equal?
Zero.
Zero. Now, if you're going to stick with the system, there's no friction. I don't have to worry about that. Okay? My force parallel is going to be
Negative 5.
So therefore, my applied force is going to be,
Positive.
everything adds up to equal to 0, I get constant velocity. Okay? Cool with that?
Yeah.
Okay. Now, clearly, if I flip it over and do this, I get a completely different acceleration like this than I do like that. So what's the difference?
Friction.
Friction. Ah! True or false? Friction will always act up the inclined plane.
False.
Why?
It acts in the opposing direction.
It just
What'd you say?
It acts in the opposing direction of motion.
That's right. Friction just acts in the opposite direction of motion. So if it's sliding down the hill, which direction is friction going to act?
upward.
Up the hill. But if I'm pushing it up the hill, friction's going to act
Down.
down the hill. So that's what, and friction is what everybody tends to screw up. So don't think, oh, everybody has this mindset that, oh, friction is always going to be a negative value, okay? Because it's in the opposite direction of motion. Sometimes it might be a negative value, okay? But get out of your minds right now that friction is always a negative value. What is always true of friction is that it acts in the opposite direction of motion, okay? That's the only thing that's always true, okay? It just acts in the opposite direction of motion. So now, we're going to change up the problem again. So, I've still got the same 1.02 kilogram block. It's still going to be on a 30-degree angle. But now I'm going to tell you that mu is 0.2. Now what's the acceleration going to be? Now let's just think this through. When there was no friction, we had an acceleration of 4.9 meters per second squared. Right?
Yeah.
True. Now there's friction. So is my acceleration going to be bigger or smaller than 4.9?
Smaller.
Smaller. Why?
Because friction's working against it.
Which direction is friction? Yeah, friction's acting against it. Okay? So now I have to worry about the friction mafia. Okay? Now I have to worry about the friction mafia. We haven't had to worry about the friction mafia before. Now we have to worry about the friction mafia. Now, I gave you mu. Remember that mu times force normal equals force friction. Now here's what you're tempted to do. Oh, it's a 1.02 kilogram block. That's 10 newtons. I'm going to take 0.2 times 10 newtons, and there's my force friction. Wrong. Wrong. Why?
Because it's at an angle.
You're on an angle. You are not on a flat surface anymore. Okay? You're not in Kansas anymore, Dorothy. You are now in Colorado where we have inclined planes. So, instead of 10 newtons, what you're going to do is you're going to calculate that force normal, which is going to be Fg cosine theta, and you can write that as mg cosine theta. It means the same thing. And what did we get when we calculated that force normal? 8.66 newtons. So now, somebody take 0.20 times 8.66 newtons. What do you get?
1.732.
So 1.73 newtons. Okay, now, at this point, this is where it's pretty critical that you take a little bit of time and make a sketch, okay? It's critical. So come in here and go, okay, here's my incline. I got my Fg, 10 newtons. Now, what do you have as your force parallel? Are we sticking with the same system?
Yes.
Are you out?
Yeah.
Okay.
Thank you.
And if you haven't had it in that lab, did anybody have any questions on the lab?
Yes.
You did? Okay,
This is like what we're going over though, right, isn't it?
yeah, pretty much, yeah. That one where it was on the incline, same idea.
Yeah.
That's why I had that transition.
Uh-huh.
Okay. You're welcome. We'll go over the assignment, so if you don't wait to hand that assignment in on Monday, or whatever you wanna do.
Okay.
Or excuse me, that lab.
Okay.
Okay. All right. So, if you're gonna stick with that force parallel being -5 newtons, okay, and that's cool. Okay, you can do that, it's -5 newtons. Here's your force normal. But, since I'm gonna let go of this thing, like this, which direction is my force friction gonna act?
Up.
Up the hill. So therefore, we have to make that a positive value. So my force friction then is gonna be 1.73 newtons, okay? Now, set up your chart. Force applied, force parallel, force friction, oh, it doesn't make any difference, your sequence, your force net. Now, again, because I've asked you to calculate the acceleration, what is your net force not gonna equal?
0.
0. So, there's no applied force, there's no push, pull, nothing like that. Don't have to worry about that. My force parallel was -5 newtons. Now, my force friction, though, is gonna be
1.73 newtons.
1.73 newtons. So I've got a -5 Newton force trying to pull it down. But then I've got my frictional mafia that's pushing against. So basically, this is one of the very few circumstances where the two mafias fight each other. So the gravity mafia is trying to pull the thing down the inclined plane. The frictional mafia is going, Tony, you don't want to go down there. You stop. So the frictional mafia is trying to keep it in place. The gravity mafia is trying to pull it down. Now, in this situation, the gravity mafia is stronger than the frictional mafia, and it's going to slide down the hill. But we can calculate this. So let's go ahead and finish up this problem. So Jackson, take -5 and add that 1.73.
-3.27.
-3 point what?
27.
Newtons.
Yep.
Okay? Now that's my net force. Now how can I get the acceleration?
Divide that mass.
Yeah, divide that by, so take -3 point, that's weird, 27 newtons, and divide that by 1.02 kilograms, and what do you get?
-3.21.
-3.21?
Yep.
What's happened to your acceleration?
It's gone down.
Gone down, why?
Because there's more opposing force.
Yeah, I have an opposing force working against it. I can't take all of that force and make it accelerate, because some of that force is working against it as the mafia. Okay? Got that. Last question. Okay? Last question. I want to push this thing up at a constant velocity. Okay? So I want to know how much force it's going to take to push this up at a constant velocity. Everything's going to stay the same. I'm still going to have the same coefficient of friction of 0.2. I'm still going to have the same 30-degree angle. Everything's going to stay the same. But here's going to be the kicker. So I want to draw this pretty big. So I still want my gravity. My force parallel is still -5 newtons. My force normal is still 8.66 newtons. Now, here's the kicker, okay? Which direction is my applied force going to act? Up or down?
Upwards.
Up. So my applied force is going to act up. So I know that's going to be some positive number. I don't know what it is, but I know it's going to be a positive number. Now, this is where friction gets tricky, okay? So if I'm pushing it up the hill at a constant velocity, which direction is my frictional force going to act?
Down.
Down the hill. This is why I said it's so critical that you draw these vectors in which direction they're gonna act. So in this case, my forced friction is gonna act down the hill. What do we get for that frictional force? 1.73?
Yes.
So now, in this situation,
It's gonna be negative.
it's gonna be negative 1.73 newtons. Okay, that's why I said, oh, friction's always negative value. Okay, might be, but guess what? Friction could also be a
Positive.
positive value depending upon how you set up your system. And that's why I said, especially on inclined planes, especially these complex problems, you have to make a sketch so that you know which direction these forces are acting. Okay, cannot emphasize this enough. So, now if you go to the chart, you got force applied, force friction, force parallel, force net. What do you want everything to add up to?
0.
0. Now, so my applied force, I don't know that value. What's the value of my force friction?
Negative 1.73.
Negative 1.73. My force parallel is going to be
Negative 5 newtons.
negative 5 newtons. So therefore, my force applied has to equal
Negative 6.73 newtons.
Not negative.
Positive 6.73 newtons.
6.73 newtons. So now what's happened, now the mafias have teamed up, okay, because now they're working together. So now, when I go to push this thing up the hill, the frictional mafia is going, man, you're going up the hill, we're going to try and slow you down. Force parallel is going, you're going up the hill, we're going to try and slow you down too. So now, instead of the mafias like fighting each other, like if it's sliding down the hill, the frictional mafia is acting up the hill, the gravity mafia is acting down the hill. But when I go to push this thing up the hill, now they've teamed up. They're going, oh, man, let's join forces. You and me, Tony. Let's get the family back together. You quick boy, okay? So now they're going, hey, well, this is what we're going to do. So now you have to fight both of them. So now you got to add them both together, okay? Does that make sense?
Yeah.
Last and final problem. I want this thing to slide down the hill at a constant velocity. Now it's going to slide down the hill at a constant velocity. Now what's going to change? Of what?
Your
Force friction.
Force friction.
Am I going to change the numeric value of my force friction?
No.
No.
And I am going to change the sign. So now, if I want the thing to slide down the hill, now this thing is sliding down the hill, am I still pushing up the hill? So it's sliding down, but
Yes.
am I still pushing up?
Yes.
Yeah, because if I push down, it's just going to go faster, right? Okay. So I've got to basically, I imagine I'm on the downhill, pushing to keep this thing from sliding down. I want to slide it down at a constant velocity. Two most important words. Net forces add up to?
0.
So if it's going to slide down at a constant velocity with friction, okay? What still do you want your net force to equal?
0.
Net force is still going to equal 0 newtons. Am I going to change the value of my force parallel? Still a negative 5 newtons, right? Okay. But now I'm pushing up, but it's sliding down. So which direction is my force friction going to act?
The opposite.
Force friction is going to be acting up again, right? So my force friction now is going to be 1.73 newtons. So now, how much upward force do I have to apply?
5. No.
Oh, just add up to 5.
4. No.
3.27.
3.27. So there's my force applied. So now, here's the deal. So when this thing is trying to slide down this inclined plane, the force friction, so here it is. So here's your setting. So you're like this, right? I want this thing to slide down at a constant velocity. So I'm actually pushing up, even though it's going down the ramp. So my force parallel is dragging it down. Because I'm going down, my force friction is up, and my applied force is up. Okay? So now, me and the Frictional Mafia, we've teamed up. Okay? Me and the Frictional Mafia, we formed a coalition. And now us together are trying to balance out the Gravity Mafia. So the Frictional Mafia, it's like it can switch sides. Sometimes it's positive, sometimes it's negative. Kind of goes with the flow. But your force parallel, your gravitational mafia is always a negative value. Okay? Got that? Yeah, literally, on these problems, either your net force equals 0 or it doesn't. Draw your forces. You're always going to have parallel, normal, gravity. Sometimes you have friction. Sometimes you have applied force. Sometimes it accelerates. Sometimes it doesn't. Sometimes you're a good boy. Sometimes you're in trouble with the mafia. Okay? Cool with that? Okay, so let's chit-chat about the lab. So let me kind of make sure you're kind of cool with what your answers should be. On that last page on problem number 5, where you've got the 200 gram mass and the 240. Now, let me explain specifically why I picked those masses. Okay? So, if this is an Atwood machine, where you have a 200 gram mass and that 240 gram mass, so if it's an Atwood machine where you're going up over the pulley, I let go of that. Which direction is it going to go? Just 240 going down, 240 going up. 240 is going down all the time, right?
Yeah.
Remember, we're going to call that the applied force. We're going to call this the opposing force. Now, here's the deal. What's different on that final set of questions on page 5? I want you to look at question number 1. So, I purposely picked the exact same masses. Okay? So, now I've got a 200 gram mass here. And now I've got that 240 gram mass that's up on the table. So this is why I picked those same masses, so that you can make this comparison. So on the pulley, the 240 and the 200, 240 is going to fall, 200 is going to go up, right?
Yeah.
Okay? But if I do this, I put the 200 on the end, the 240 up there, what's going to happen?
200 will fall.
200 is going to fall. So over here, 200 goes up. Over here, 200 goes down. What's the difference? Same masses. Why does one fall and the other one doesn't?
One has force normal.
This one is balanced out by the table and has normal force. This one doesn't. Okay? And here's the difference. This one, we're calling the 240 the applied force, and we're calling the 200 the opposing force. Okay? This one, this is just the applied force. The only way that there could be an opposing force here, if it's flat, is if there's friction. So that's what I want you to look at on question number 3. So on number 3 I said, however, the coefficient of friction, the 240 is actually 0.1. What's the frictional force impeding the motion of the 240 gram block? Listen to me very, very carefully. Friction is only determined by this contact right here. This mass out here has nothing to do with this calculation of frictional force. You could put the elephant out here on the end of this string. It's not going to affect the frictional force here. So when you're looking at this frictional force, only isolate this system, okay? Don't let that be a part of it. It doesn't matter, okay? Not part of the story at all. This is the story when it comes to friction, okay? So, now think about this. If this thing is pulling down, still with the force of 1.96 newtons, that's still my applied force. Now, what are you going to have? What's different?
Do you have an opposing force?
What'd you say?
Do you have an opposing force?
now I have an opposing force. Oh, same applied force, now I have an opposing force. What's that going to do to my net force?
Decrease it.
Make it smaller, so what's going to happen to your acceleration?
Decrease.
So your acceleration on number 1 would make a very, 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 very good weighted GPA. Okay, but it's got to be a weighted GPA scale. Your acceleration on number 4 should be around 4. Okay, so on number 1, the acceleration is around 4.5. On number 4, that acceleration is around 4. Okay, now hopefully what you see is why that happened. Okay, it happened because I kept the same applied force, but then I had an opposing force. And that's what I wanted you to see when you took that incline and you put the board underneath it. You should see that your acceleration became less. Because, oh, now we had the same applied force on the end of the string, but then we had an opposing force, which is now what we're calling an inclined plane, and we're going to call that force parallel. Okay, but that's why I had that in there as a segue between the two of them. On question number 2 on that last page, there's different ways you can do this. But at the end of the day, you're going to have 2 different masses. Mass on the end of the string, mass up on the table. So you can call it M sub H, mass hanging, MT, mass on the table. Mass 1, mass 2, mass red, mass blue. I don't care. But what is important is that I know how you're defining your masses. Okay? So if you're going to put this as MH, what does that mean? I don't know. So what I want you to do on that question number 2 is that you should be able to take your paper and give it to someone and go, hey, this is how we calculate acceleration problems on an incline on a surface like this, where you have one that's hanging and one that's up on the table. It's a generic one that you should be able to use in any situation. Okay? So if you're not sure if you're right, give it to a classmate and go, hey, you know what's going on. Can you look at this and know what I'm talking about? And if your classmates go, I don't even know what you got going on, that's bad. Okay? If your classmates look at it and go, okay, yeah, that makes sense, then we're good. Okay. Did that clarify that? Any other questions on the lab?
No.
Okay, we're good. Okay, so if you have the lab done, hand that in. If you need some time to finish that up, hand that in on Monday. And then here is the assignment that is due on Monday.
Thank you.
I hate Wednesdays. I always think about it like 2 Okay.